Okay. All right, section 6.1, perpendicular and angle bisectors. Our objective for this lesson is to use perpendicular bisectors to find measures, use angle bisectors to find measures and distance relationships, and then we're going to do writing some equations for perpendicular bisectors. Okay. So first we need to talk about what perpendicular bisector is. Okay, so, and really the word perpendicular bisector says exactly what it is as long as you know what these two words mean. Perpendicular, this part here, intersect at 90 degrees. Bisectors at its midpoint. Okay, so basically if I have a segment, AB, the perpendicular bisector is going to intersect this segment at 90 degrees at its midpoint. So here, we say this is point M, is its midpoint. So to note its midpoint, I'm going to put a notch on either side to show these two pieces are the same. So M's there, the midpoint, and we'll intersect here at 90 degrees. So here I have the line, intersects at 90 degrees. Okay, so here we have, there's our perpendicular bisector. So we know it's perpendicular because of this little square here, and we know it's the bisector because of the two notches. So you need to know that it's 90 degrees and it goes through the midpoint. Okay, all right, if you remember, we talked about equidistant, I think before, but equidistant just means equal distance. Okay, so a point is equidistant when it is the same distance from each figure. So the same distance from each figure. Okay, so if I say I'm equidistant, my house is equidistant from McIntosh and McLaughlin. It means I'm the same distance from both McIntosh and McLaughlin. And again, remember, we measure distance from a point. Distance from a point is the perpendicular distance. Again, that's our symbol for perpendicular again, if you don't remember. So distance from a point is perpendicular. Okay, so if I wanted to measure the distance from this point, let's say this point X, to this line, I wouldn't measure the distance like this. The distance would be this perpendicular distance. That distance is always a perpendicular distance. There's my distance D. Okay. All right, so now we have actually a new theorem today. I think we'll have 2 new theorems total. Okay, but then also it's converse. Again, if you don't remember, it's converse. Converse switches the P and the Q. The hypothesis and conclusion switch spots. Hypothesis and conclusion switch spots. Okay. So here, perpendicular bisector theorem in a plane. So this is restricted to a single plane. Okay, it's not in space, all over in space. It's here flat on the plane. If a point lies on the perpendicular bisector of a segment. So, if I know here, if I know C is on the perpendicular bisector of this segment, which I can tell we have perpendicular bisector here because there's a perpendicular part, the two notches make it the bisector part. So, if a point lies on the perpendicular bisector, then it is equidistant from the endpoints of the segment. So meaning now this distance from C to A and from C to B is the same. We know that. So if C is on the perpendicular bisector, we're going to shorten that up, of segment AB, segment AB, then I know the distance from C to A is the same as the distance from C to B. Because if you notice, A and B there are the endpoints of the segment. Okay, so that's our perpendicular bisector theorem. Okay, the converse really flips these two things around. Meaning, if I know that I have some point here, if a point is equidistant from the endpoints of a segment. So if I know that DA is equal to DB, so DA is equal to DB, then I know, then D is on the perpendicular bisector of segment AB. Then I know D would be on this perpendicular bisector. So this perpendicular bisector then would go through D, if I know that those are equidistant. Okay, all right, so we can use this to actually find missing pieces if we know. So first we have to know which theorem are we using. Do we know we have a perpendicular bisector, or are we implying, or are we proving that there's a perpendicular bisector? Okay, so here let's look at the information they give you. They tell me this is a 90-degree angle, so that's perpendicular to this segment, and they tell me that these two pieces are the same, which tells me that this line right here, this line, that highlighted line, is a perpendicular bisector. This is a perpendicular bisector. Okay, so since it's a perpendicular bisector, here we have a point on this perpendicular bisector. Our goal is to find RS. We want to find the distance, RS. We want to find the distance from R to S. We want to find that distance right there, that green distance. But S here, we know, is on this perpendicular bisector. Well, if a point is on the perpendicular bisector, then it's equidistant from each endpoint. So then I know that SP has to equal SR, or RS. RS has to equal PS. I know RS has to equal PS. We know PS is 6.8, so RS has to equal 6.8 because S is on the perpendicular bisector. So this is using the perpendicular bisector theorem. By the perpendicular bisector theorem. Okay, so it doesn't say to explain why, but that's always a good habit to get into. Okay, all right, so let's look at the next one. We want to find EG. So our goal is to figure out the distance from E to G, that whole distance right there. Okay, well, I know F to G is 9.5, but I don't know this E to F. We don't know that distance right there, E to F. Okay, but I do know that, let's see, H here, H to G is 24 and H to E is 24, so these two are the same. So I have a point that's the same distance to the endpoints of the segment. If a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector. So since HG is congruent to HE, so we know HG, well, we'll just not use a segment, we'll just say the distance from H to G is equal to the distance from H to E. So then I know that this line, so we know then that line HF, that line is a perpendicular bisector. Well, since it's a perpendicular bisector, we know it is perpendicular, which we have that 90, but we also know bisect, which means that this segment is the same as this one. So then I know if F to G is 9.5, then F to E is 9.5. Well, that means that E to G would be equal to EF plus FG, segment addition postulate. Well, EF is 9.5, FG is 9.5. You add those guys up, 9.5 and 9.5, 18, plus one more, 19. So E to G is 19. Okay. Last example here before I move on to something else. Okay, all right, so let's look at this one. They want us to find AD. So A to D, that's this distance right here, A to D. Well, we know it's 5x, but can we get a number for it? Okay, all right, let's see, what do we know? What's given? We know C to D is 3x plus 14, D to A is 5x. We know B to C and B to A are the same, both one notch. Oh, so we have a bisector. We also have a 90 degree. So we have a perpendicular bisector. We know here that this is a perpendicular bisector. Well, if that's a perpendicular bisector, then that means D is the same distance from both endpoints. So this segment and this segment are the same. If they're the same, the measures are equal. So I know 3x plus 14 has to equal 5x. If we subtract 3x from both sides, we'd get 14 equals 2x. Divide both sides by 2, x would equal 7. So if x equals 7, again, we're trying to find a to d. A to d is 5x. We know x is 7, so that would be 5 times 7, which gives us 35. Okay, and that was again using the perpendicular bisector theorem. This one in the middle here, this b, we use the converse because we didn't know that it was perpendicular or we didn't know it was a bisector until we knew these two pieces were the same. Okay. All right, next. Okay. All right, example 2. Is there enough information in the diagram to conclude that the point N lies on the perpendicular bisector of KM? So we're trying to figure out, does it lie on the perpendicular bisector? So we're looking for perpendicular bisector. So what I'm going to do is I'm going to sketch. I'm just going to draw a sketch of what's happening outside of the picture. So here's K, M, and N, and then we have L coming down the middle here. There's L. They tell me that if you notice there's one notch here, K to L is the same as L to M. Okay, so we have the bisector part. We know it's a bisector because of the two notches, because I know L is the midpoint. So we know the bisector. Do we know the perpendicular? Well, do they have a little 90-degree angle in there? No. So I don't know it based on just the information they give me. Is a point equidistant from the endpoints of a segment? Okay. So here, if we look at N, do they tell me the distance from N to M is the same as the distance from N to K? N to M, nope, no notch there. N to K, nope, no notch there. So is there enough information? No, there isn't. What else would we need to know? We would need either that N to M equals N to K, or that the measure of angle MLN is 90 degrees. Okay. We would need to know this is 90 degrees, or that these two segments were the same, depending on what information we had. So it doesn't say what other information you need to know, but again, it's always good to be thinking of that. What next? If I was having to prove it, what else would I need? Okay. All right. Okay, a little more review. We talked about an angle bisector before. Hey, an angle bisector. Again, bisector like goes through the midpoint or divides it into two exact, divides into two congruent pieces. Okay. So an angle bisector, what an angle bisector does is if we have an angle here. So there's my angle. Okay. Let's call this angle ABC. ABC, like that. What an angle bisector would do is an angle bisector would be a ray or a line that comes through here, let's say goes to D, and divides this into two congruent angles. Okay. So BD, ray BD would be the angle bisector. Okay, so BD is the angle bisector because angle ABD, ABD, that's its top half, A to B to D, its top half is congruent to angle D to B to C. The bottom half, D to B to C. Okay, if it divides it into two equal pieces. Okay, all right. Okay, if a point lies, so here we have our other new theorem. We only have two new theorems and their converses. So if a point lies on the bisector of an angle, Hey, so if a point lies on the bisector of an angle, so here again, here I have an angle. Here's my bisector, meaning if I know this, if I know that, then, so I have a point that lies here on the bisector. Let's call this point M. Okay, then this point is equidistant from the two sides of the angle, meaning this distance from this point to this side is the same as this distance to this point. But again, remember we measure that distance perpendicularly. So it would be this distance here, this perpendicular distance. That distance, let's say M to A, is the same as the perpendicular distance. Let's go B. So we know if M lies on this angle bisector, then M to A equals M to B. It's again that perpendicular distance. Okay, so that's here what they have in this picture here. Again, we have angle BAC, and then we know AD is the angle bisector, and the reason we know angle bisector is because of these two pieces. Those arcs let us know that it's an angle bisector. So I know D to B is the same as D to C. That, again, perpendicular distance. Has to be 90 degrees. If we didn't know that 90 degrees, then we wouldn't know that they're the same. So we know this piece and this piece are the same. The converse, again, just flips up the hypothesis and conclusion. If a point is in the interior, so you have a point inside an angle, and it's equidistant from the two sides, then I know that D lies on the angle bisector of angle A. Okay, so since we know that DB is congruent to DC, again, we have to know congruence and that it's 90 degrees, because if it's not 90 degrees, then we can't use this theorem. But then we know that ray AD is the angle bisector of angle A. Is the angle bisector of angle BAC. Or basically, we know that these two angles in there are congruent. Okay. Right. So here, find each measure. So here we want to find the measure of angle GFJ. So, the measure of angle, there we go. The measure of angle G to F to J. So we're looking for that angle right there. We know this little angle is 42. Okay, we're trying to figure out what's this angle in here. What's that little angle in there? But we know J to G is 7, J to H is 7, so they're congruent. We also know that it makes a 90-degree angle. So I know J is equidistant from these two sides. If a point is in the interior of an angle and is equidistant from the two sides, so here J is inside this angle, it's equidistant from these two sides, then it lies on the bisector. So then I know that FJ is a bisector, which means these two angles here are congruent. So if this one's 42, then this one's 42. So the measure of angle GFJ is 42 degrees. And this was using the converse of the angle bisector theorem. Okay. And now, last example, we want to find the distance from R to S. R to S is that distance right there. Okay. Let's look at our picture, see what we know. We know that this angle and this angle are the same. They both have one arc. So I know then that ray QS is an angle bisector. I'm going to use the symbol. So since this is an angle bisector, any point on this angle bisector is equidistant. Well, we know this is 90 degrees. Again, we have to know that perpendicular part, so I know these two things are congruent. So I know 5x has to equal 6x minus 5. Let's subtract 6x from both sides, so that gives me negative x equals negative 5. Divide both sides by the negative 1, x equals 5. So I know x equals 5. So since x equals 5, I can find RS, because I would take RS equals 6x minus 5. We know x is 5, so 6 times 5 minus 5. 6 times 5 is 30 minus 5 is 25. So R to S is 25. Okay, we have one more example. It will be in the next video.